All right, can you hear me? Everyone? Let me see, make sure that it's.
We can hear you, Professor.
All right, thank you. Okay, so just a couple of things. There have been some questions about homework, and I wanted to just clarify what I suggest that you do in the homework. So this is, I believe, the team homework in it. All right. Okay. So what I would do is that I would divide, all right, so the current flows here and there, and I say semi-infinite because here it continues forever, all right, and somewhere, this wire somewhere at infinity connects, so there is a closed loop, but it comes here like this. And then it goes around like that. This is like half a circle, like this one. And then another half here, practically. We have said that this section is not contributing because it's small. This one, I mean, I put them at this distance because I could not make them smaller. But this is so small so that the field that's concentrating here does not contribute compared to this one. All right, we talked about that when we had the loop. Remember, we found the inductance in the loop. So you divide this into 3 sections. You find the field here from here. You find the field there from there. And you find all of the, because there is no, the current continues here, is as if all of the points here, they see these 2 lines as they are like infinite long. And then so you use the circle here, the formula for this, but it's half. You use the formula for these 2 parallel wires that we found. You use the formula for another half circle. And then for this, from here you find this point, from here you find this point, and from these 2 you find this point. And as we have discussed, when you try to find the inductance, just to remind you things that we have seen, all right? When you try to find the inductance, you remember what we said? That when you look at the flux density line, I mean values, all right? So that like a B, the magnetic flux density B. When you look at how it varies, it goes almost to infinite when you're very close to this, but then it goes down quickly. And then, because there is cancellations, not just that it goes down because of the distance away, but because there is cancellation outside. That is outside of these 2 wires, there is cancellation, all right, of the field. And then the field sums up, we have talked about this multiple times, right? The field sums up here. So cancellation out here, but the field from the 2 lines sums up here. So you see this here, you see that here. And when you try to find the flux, the contributions from these infinite like sections goes to 0. So practically, you remember what we said, when you are to find the flux for this one, you take this value at the center, and then it's an approximation, obviously. You don't go to the computer, but you take the value that you have at the center along the axis, and you multiply, and then you assume that this value applies across. What did we say about the loop? A similar kind of thing. All right. In the loop, we said if you have a loop like this, these are things that we just go and review the material that we covered for this. That's the reason I gave you that too. If you have a loop, let's assume the loop is like that. Okay. And then you have a current that flows.
And if you plot, if you take a cross section here of the loop like this, all right, then practically I see this line here and this is the cross section of the loop. I see the two lines. All right, so the current flows like this in one line, flows like this in the other line. So it goes in the board here, out of the board here. And how does the field look like? The same kind of thing. There is cancellation out here, strong cancellation, and out here. And not like this, excuse me. And here. And then it goes like that inside. Well, a little better than this. It goes like this. All right. And then we said, when you try to find this is the flux density, magnetic flux density along this cross section. And then if you try to integrate here, practically, if you try to, this applies on every cross section, applies along like this too, all right? I mean, everywhere, if you go around this loop, you're gonna see something like that along the diameter that goes through these 2 points. Okay, so when you try to integrate, these cancel out, these cancel out, and then practically it makes it approximately, all right, that seems approximately. The flux is similar to as if you had the circle here, maybe, let me just do it, the circle here. But the assumption we've made is for the flux only, magnetic flux rather. For the flux only, the assumption we make is that we take this point here, we assume that this is constant, so practically the assumption is that's for magnetic flux. The assumption is that approximately the magnetic flux density looks like this, where this is the value at the center. Okay, that's what we are we have discussed in the past. That's how we found, all right, an inductance for a loop. You remember when we did those things? Go back and review those. So practically, this is exactly the approach you're going to use, but now you have to and then you have to combine this. You find the value here at this point is what you find from the half circle. The value at this point is what you find for the other half circle. They're identical. And the value at every point along this green line here is what you find from the infinite parallel lines. So then you have the values you have to compare. There is one where I ask you to compare these two values with this, which is practically all the values along the line. And then you will see, I'm not going to tell you what you're going to find, but you're going to see what you're going to find. And then you can take these values and then you use this to find the flux in the two red sections in the green one, and then you sum it up. And then you divide by the current, and then you find the inductance. Any questions about this? It's like a synthesis. We took pieces that we have seen and you put them together. All right? Okay. Now, last time we did the matched line as an example, and then I will not cover this again, but what do you remember what we found when we look, first of all, what do we call matched line? Is when Z naught, the load,
becomes the same with the characteristic impedance. Remember that? Last time you were a little tired. That's why I remember that very vividly. Or it was the day before. I don't remember, but one of these. In any case, Z naught, the load becomes equal to the characteristic impedance of the line. We solved this problem, and you have it in your notes in the module, exactly like this. And what did we find? We found, first of all, that everywhere the reflection coefficient on the line is 0. Remember that? So that's why it's called matched. Why is it called matched? Because it does not have a reflection. It does not have a reflected wave, the negative wave. Right? You remember that on every voltage, we have two components here. Remember that? We have two components in the voltage. The first one, we call it the incident wave, the B plus. The other one, we call it the negative wave, the reflected wave, the B minus. And because of how we define the reflection coefficient, the way we define it, let me see. Here, the reflection coefficient then becomes 0. What does that mean? That every place that has the V naught minus here is 0, and in the current too, all right? So V naught minus does not exist, 0, which means that the negative wave, which is the reflected, is 0. Therefore, it's only an incident wave. So there is no reflection from the load, which is good news because all of the power that you send in the line is absorbed by the load. So in all cases, when we design, like in high frequency circuits, we try to move energy from the source to whatever circuit we connect. You remember all of these lines that you have seen in the pictures that I'm giving you? I'm showing you. Those lines are trying to connect an amplifier or an oscillator or a filter of some sort to the point where you have your incoming voltage, which is an AC. And you want to make sure that the line you're using is matched totally to the load. Usually, the loads are not real. The loads can, in general, are inductive as well, or capacitive. All right, so a input impedance to a low noise amplifier is not always real. The input impedance to a filter might be real, resistive, but it's not Z0. So what you have to do in your design, either you design those components to give you Z0, which is not always possible, or you put a circuit in between this component and your transmission line, which we call the matching circuit, to really match eventually, right, your line to whatever it sees at the end. So we'll see those matching circuits we're going to design. We're not going to design LNAs in this class. That's in 453, but we are going to design the matching circuits here. They're very fundamental, right? So that's why this line is matched, because obviously the real load was something different, was a ZL. We put something in between the load and the line, and we created then a total impedance seen here at the end. There was enough, and that's a matched line, and gives you 0 reflection. Okay, that's what we saw last time. Now we're gonna do something more general. And again, same kind of equations. I also have to tell you, after we do these equations, and then we arrive at specific formulas that I'm going to highlight for you, we're not gonna re-derive them again unless I ask you some specific things. You will see in the examples we're gonna solve. Most of the time, when we design circuits, all right, we don't have to go through the same analysis.
But now I'm gonna go again through it so you get more comfortable. I'm not gonna skip steps. You see it again. And in this case now, what we are solving is a general load, Isabel. And I'm gonna do that because if you find the expressions for the general load, then we can do this, the maths, we can do the open-ended line, we can do the short circuit line, you can do everything. All right, so we are gonna do the most general case. All right. Now, again, one thing that I want to tell you, in this, there is a catch in these types of problems. Yeah, the problems themselves are not intellectually difficult. They don't have a lot of math. They don't have integrals. They don't have their derivatives. They don't have these kind of things that you may find in statics. However, because it's so many things in there, people can get very confused early on. So here is what I will ask you to do every time you solve a problem like this, in homework or in the final. I would like you to redraw the circuit. Redraw it, what I'm giving you. And I will give you points for redrawing the circuit. It has to be nice, clean, like this. Not some of the things that I showed you last time, right? I'm gonna give you points for presentation too, starting from this homework that we're gonna start this coming home. This, I mean, the one that I'm gonna give you next. Why is this important? There are so many things. So for example, you also need to remember what I give you and what you know. So the process here, I would like you to follow. So you do the circuit, you put your load, the length, you put the things here, always Z naught and beta to remember. You put your source, and usually the source has an internal impedance. You've heard those, right? From circuit. Source always has something. Okay. F and lambda. I will give you one or the other, not both. We said why? Because if you know one, it gives you the other. If I give you both and then they don't satisfy this equation, then there is something wrong. So I'll give you one or the other. Or if I give you both for some reason, I will make sure that this is satisfied, but usually one or the other. Okay, I will give you Vs. Always, I will give you this a best. That's a source. We get it. We borrow it from somewhere else. And then, in this particular problem, I give you this a bell. All right, so I put here everything that is given. And then, 1, 2, and then you remember, always you're gonna put the nodes, input port, output port. Right? You're gonna always make sure you know where yours equals 0, when yours equals L. All right. Then the question, there's one question here. I'm asking you to find the input impedance at A prime. All right, and now we're gonna put down the things that we know before. This is of course a lecture today, so I will give you some new definitions, but before you start solving the problem, you're gonna write down what I gave you and what you know, which are useful in the solution. And then you're gonna go and solve it. So solution says no. What do we know on this line that we have defined? That the input impedance at any point on the line is the ratio of the voltage at that point on the line divided by the current. So at any point on the line here, Z. The input impedance at this point, and many times I show input impedance with yellow. So many times, many times you're gonna see that we usually in lines, always, we show the input impedance here like this. all right?
So it's always a line like that.
And I'll come to this. The reflection coefficient, usually we show, you will see there are some visual things that we use. Okay. So we know that. All right. So practically, also I'll show you some other notations that we use here. When you have the input impedance and at any point which is not necessarily defined, you write it like that. Z input of Z. However, your input impedance at specifically defined nodes, you write them as Z input slash at AA prime. All right, that is clearly to remember where your input impedance. This is how I'm doing it. And the books, different books do different things. But if you follow this, you will never really forget what you're dealing with. All right, so I call the input impedance at A prime as Z input at AA prime. All right, then Z is a bell. It's your load. L stands for load. And according to Ohm's law, this load here is the ratio of the voltage, total voltage at VB prime divided by the current at VB prime. And see how I indicate those voltages and currents? Because there are at particular points, I put the two nodes, VB prime, IVB prime. So I don't have any, questions about where this voltage and current is. Okay. And the input impedance at this point, AA prime, which is right here, is the ratio of the voltage at AA prime divided by the current at AA prime. Okay? So now, what else do we know? We wrote the first thing, all right? In fact, what I will do here to help you visually with this, I'll give some distance in between those things. Okay, put them in a distance. Otherwise it gets too crowded. All right. So we talked about the first one here. Now we go to the second, which is something that we have seen before. We write the general expressions for voltage and current. These are things that you know, all right? These are the things that we have discussed. Why do you do the Z input at Z? Because my question is around input impedance. So you really have to write those so you know, you remember what the input impedance is at the various points on your line is, usually at the nodes, AA prime, BB prime. This one here is the voltage and the current inside the line, all right? And we know, we have seen this. It's the total voltage at any point on the line is the sum of two voltages, the incident, and in fact, I can put this red, and the reflected. All right? These are the two voltages. All right. So I write it here. Okay, we know that. Then I write the current because in these relationships, I need the current. I cannot find any input impedance without knowing the current. So you have to write the current. And the current that you see from the expressions we've had, I'm using the one that has only the V naught plus and the V naught minus. And I use this relationship, if you remember from before, that allows me to replace V naught minus, I naught plus and I naught minus with V naught plus and V naught minus and Z naught. So you see here this Z naught in front of the
brackets, Z naught. And then this is the incident voltage, but there is a minus here. There is a plus in the voltage, there is a minus in the current with the substitutions, and thus they reflect. So now I wrote this, but also in terms of incident and reflect.
Okay. Now, some new, these are things that we have seen. New definitions. Now,
I put them in pink because it's new. Reflection coefficient, gamma Z. The reflection coefficient
is a new parameter that
relates the reflected wave to the incident. Z naught reflects either incident or reflected waves, but between voltages and currents. All right. Z naught reflects wave voltage with current, but reflection coefficient relates reflected voltage to reflected current. All right. And this is called the voltage reflection coefficient. For us, we are going to only use the voltage reflection coefficient because there are, if you go, say, to look at anything on the web, people may define a reflection coefficient in terms of current, and they call it the current reflection coefficient. So be careful when you write expressions about the reflection coefficient to make sure that is the voltage reflection coefficient. That's what we are using. Don't just blindly go and copy something. All right, make sure that you read what it is all about. Okay.
and in this one, obviously, this is the reflection coefficient. In this reflection coefficient, we have now
Use this definition. We have used this total, the incident wave, which in fact you can write it in this form. All right, we have seen that. And the reflected wave, you can write it in the other form. You see, I wrote these equations 4 and 5. So now, if I take 4 and 5 and I put those into 3,
what do I get? I get this new expression for the reflection coefficient everywhere on the line. All right, this happens everywhere on the line, at every Z point on the line. I see
the reflection coefficient to be the ratio of these two constants times an exponential. Okay? All right, so now I can also write here something else.
what that tells you is if let me observe something here. From the matching, you remember that we defined the reflection coefficient at the input. The reflection coefficient at the input A prime, right there. Now, also I need to tell you that at any point, say you go to BB prime, usually we show the reflection coefficient like this. I always show the reflection coefficient because to remind you
that the reflection coefficient shows reflection. All right, so I always show it like that. Visually, it's easy to differentiate. We show Z input like that, we show gamma like this.
And in fact, if you wanna also find it somewhere and you cannot have enough space to do this, say at ZZ prime, to put there the reflection coefficient, make it a little smaller there, this one. You know what I would do if I want to write here the reflection coefficient? I can put it over. So I can put it like that and then show that this is the reflection coefficient at Z. See?
So I remember what I'm using. Okay. So also here, even if this part is circuit and this part is circuit, you also can define a reflection coefficient in A prime. In fact, there the line stops, obviously, all right? So there is no reflection towards the source, I mean, because you are in simple circuit form. However, when z equals 0, the value at that point of your gamma z is, let me write it here, gamma at z equals 0, which is gamma at A prime, all right, equal to what? V0 minus over V0 plus. So if I call this 7 and I put this into also another box, remember it? Okay. That tells me from these two something very interesting. That gamma at any point on the line is equal to gamma at 0 e to the j to beta z. That's 1. All right. Now, you remember that. What does that tell you? That if I move along the line, the only thing that I do to the reflection coefficient is to change its phase. All right? This is the phase to beta z. So the only thing that I'm doing is to change its phase. And as a matter of fact, yeah. So gamma at any point is the magnitude of gamma at 0 and has a different phase, all right? So in fact, you can write this gamma at 0. Okay, now, I also wanted, I will put this on one side, make this a little smaller, because I wanted to show you something else too. The reason I wanted to show you all of these things is because if you know those, then you can use them accordingly. You can use whatever formula helps you in the solution. So let me put this here. And now I can also do the following. If I go at gamma BB prime, if I look, let me write gamma at BB prime. Okay. At gamma at BB prime, let me in fact also do something. I need to save some space there. And since I have that down here, let me see, move this a little smaller and put this here. Okay, so why am I doing this like that? Because this way on this side, you have the reflection coefficient anywhere on the line, but is in terms of the reflection coefficient in the front where the source is. So, and I will say here reflection coefficient or gamma instead of, let me see, gamma at z. I want to save space. I'm not going to write it the whole thing. I'm not going to have space for that. So I'm going to write gamma at z as a function of gamma at 0. Okay, so that is
there. Right here, here, and here. Now I will do something else. I'm gonna go and look at the reflection coefficient at the end of the line. So let's assume that now I am at z equals 0, z equals L. So let me erase also this and put this here. And then where z, so gamma at 0, also to remind you, you can also see it as gamma at a prime. Okay. So now we are going to the end of the line. In the end of the line, we have gamma at L, z equals L, which I also indicate either as gamma of BB prime, or in our case, I can also call it gamma sub L. Okay, so whenever you see that, as long as you remember what you're doing personally, if you are very experienced in remembering that BB prime is at the end of the line, we can use gamma sub L. But as you try to do things systematically, make sure that you name it by the nodes you have. Okay, so that is at the end. At the end, according to the definition of the reflection coefficient, number 3, which is here, what do we have? That gamma at the end of the line is going to be V minus, when Z is at the end of the line, divided by V plus, when the Z is at the end of the line. And this is equal to B naught minus over B naught plus e to the j to beta L. All right, you see that? Okay. But then I have that gamma sub z now, and this is also, I can call it gamma B prime or gamma L. Okay, so gamma sub z now, I would like to write it in terms of gamma B prime or gamma L. So here I'm gonna, from the above, I will do the following. I'm going to use, okay, let me see this, V naught minus over V naught plus is equal to gamma B prime at the end of the line, e to the minus j to beta L. You see that? Okay, and therefore, the reflection coefficient in the beginning of the line is equal to the reflection coefficient at the end of the line, all right? And has this phase difference between the two. That's a very important relationship, because you can quickly go, if you have that relationship in mind, you can quickly go from one reflection coefficient at the load to the reflection coefficient at the source. And that is important to have that in mind, okay? L is the length of the line. Or you can rewrite that underneath it as gamma BB prime, which is the load. You can also remember that gamma L is equal to gamma AA prime e to the j2 by L to beta L, and gamma AA prime is gamma at the source. Sometimes you will see it like that, e to the j beta L. And these expressions, you're going to see them when you develop, you go to more active circuits, and then you remember source, you remember load, for example. But this is, in fact, the same equations back and forth. That's all that you do. All right. So you remember that. Remember always that as you move on the line, the only thing that changes in the reflection coefficient is the phase, not the amplitude. Okay. And now we're going to find out what changes, what is responsible for the amplitude of the reflection coefficient. Okay. So let me, in fact, do the following here. Let me see here. These are, well, let's find the input impedance first of all, and then we'll continue. So now all of this is, I did this very carefully because I wanted, it's a lecture, I wanted to remember those things and how they are derived. But the formulas here, I don't want you to rederive them. I want you maybe write them on one together, on one table, and look at the table all the time as opposed to going through different pages, all right? That's what I would do. These are what I have in these squares, is what I want you to have available. Eventually, you're going to remember it by heart. Now, the problem in our problem is asking to find the reflection, the input impedance at, what does it say? At AA prime. Okay, so now I want to remember how we define the input impedance. The input impedance is defined as the ratio at any point on the line, as the ratio of this, the voltage wave at that point divided by the current at that point. Right? What is the voltage at that point? Is the incident plus the reflected. We've seen this before. Okay? Now that I have defined the reflection coefficient, see how else I can write the total voltage here. I can write it as, and in fact here, just to help, I will put it here. And then I will put that into a square. So you guys remember it. Put it together. Okay. So you can write now the voltage in terms of the reflection coefficient. See? And then you will do the same thing with the current. So why am I doing that? Because now I can write the voltage, the voltage and current in terms of reflection coefficient, and then the impedance eventually. So the same thing with 7. Probably 3. Put 7 here. Let's put here 8. 8 here. I can do the same thing for the current. Call that 9 here. Okay, and then I will write it also as I of Z. Therefore, I can write it in the form that involves the reflection coefficient. Okay, that's another one to remember, at least to have available, not to remember by heart necessarily, but to have easily available. So what I would do if I were you, go and put all of these important formulas on a piece of, on a table, piece of paper, whatever it is useful, on a table, an Excel file, do it whatever you want and have them available when you solve problems. Okay, so now if I take 8 and 9 and I plug them in where I have defined the input impedance, what can I do is find a new expression for the input impedance, which is in the form of the reflection coefficient. That's very important. Okay, reflection. So this is a very important, the most important of all, if there is such a thing. this is an important expression that I want you to have in mind and always remember it. Oops, no. This one. All right, this one. I want you to remember it. This is what gives you the input impedance in terms of the reflection coefficient. So if you know one, what is the interesting? If you find the reflection coefficient at any of the ends of the line, then you know the reflection coefficient at every point on the line, and then you know the input impedance at every point on the line. So the only thing you have to do is to find the reflection coefficient. That's the only thing that you need to do. And everything else is there. All right, with all of these, therefore, derivations, the only thing that we've learned, and I will write it here, put one page, is you need to remember, let me see, where here, other page. So, wrong place for the page, but I. What happened? Wrong. Okay, let me put it there. That's okay. Leave it there. I'm supposed to. But it's there. Here, I'm supposed to put a page. Here. Add. Okay, so from here, we have something, I will write it here so you remember it. So from 10, you know that if you find gamma of z, then you know z input of z. That's from 10. And from before, look at these two expressions for the reflection coefficient, here and here, or this one, all right? It tells you, and also, if you know gamma at the source or gamma L at load, then you know gamma at Z everywhere. All right, if you look at this, what is the conclusion? That to find Z input everywhere, therefore to find Z input of Z, what do you have to do is find either gamma L at the load, or if you can, gamma S. All right, and that's it. Because from gamma L, you know that your gamma Z is your gamma L e to the minus, let me just make sure, yes, minus J 2 beta L L is the length of the line. And then also we have the Z input equals Z naught 1 plus gamma L e to the minus j to beta L divided by 1 minus gamma L e to the minus j to beta L. Okay, so that is important to remember. So practically, what would be the solution to all of this problem? The solution to all of this problem is here. That's how short your solution is if you know everything that I told you previously, which now you know, you have to have available. So now if I were to give you the same problem and ask you to find the input at A prime, then you will use these formulas to find it. All right? At this point, I'll stop. And then next time, having this, we are going to be able to solve the input impedance everywhere for every load. And then we'll see some interesting things, especially for the matched, of course, is 0. The matched, and then what happens if gamma L is 0 from here? The matched gives 0 reflection. And what happens to the input impedance everywhere? Is equal to characteristic impedance. See, you see that, I mean, this is the only thing that you need to have practice in this problem. That's all it comes down to, 2 equations. Yes, it does. But you have to know the before, all right, to be able to use them. So in any case, next time on Monday, we're going to start with, we're going to do different loads. That's what then now our examples will come into play. You can, what did I do next before I forget? Let me, top hat. Yes, thank you. So here, there, no, top hat. Okay, 502. Okay, I found the top hat I'm gonna give you. Do you know what it says? I don't know what that is, but it's the big. It says, consider an idea. Well, anyways, you're gonna see it. I'm gonna sign it for Monday. Okay. Now you will be able to solve it easily. All right. Somebody already did that. Okay. I don't want to show to you, everybody what is happening.